notes. What is this? Is this 21 or 22? 22. Okay. So we're gonna, as I said, we're gonna do two sections, 7.3 and 7.4. 7.3 is another integration technique called partial fractions, and then 7.4 we're gonna get into what we call improper integrals. Basically, integrals involving infinity. So don't worry about that right now. First, let's just attack this idea of partial fractions. Basically, if you think about partial fractions, you're going to be dealing with integrals that you have a fraction, or in other words, a rational expression. So, for example, this problem. We'll do this example here. Okay, now, always try everything else first. Use substitution. If you let u equal the denominator, no, derivative's not going to cancel the top. You know, there's nothing going on. You could try to simplify, cancel, back cancel, but it's not going to work out. Okay, so then you realize, hey, I got a fraction. Maybe I'm going to do partial fractions. In other words, split it into two fractions being added together that would be equivalent to this fraction. The first step to do that would be to factor the denominator. This would only work if you can get the denominator down to two things being multiplied together. So we're just going to keep 4x plus 41 on the top. We're going to factor out the denominator. We get x, we get x. Factors a negative 10, add up to 3. So plus 3 and minus 2. Or excuse me, plus 5 and minus 2. Alright? Now, the next step is to rewrite this as an integral of two fractions being added together. So we're going to actually go backwards from getting a common denominator. We're going to break it apart. That's why we call it partial fractions. But we want it to be equivalent. Our two denominators, one will be the x plus 5, and one will be the x minus 2. Now, what you can't do is just cut it in half and draw a line between the two and put 4x over x plus 5 here and 41 over x minus 2 over here. Okay? You can't do that, even though some of you will try. People do try. Maybe you won't try, but other people try. Got it? That's not algebraically equivalent. But there is a way to figure out what should be here. So we'll just let that be A and let that be B for now, because we'll find out what those values should be in order for this to be equivalent. If I was going to go backwards, I get a common denominator, and I would do that by this. The first one is only x plus 5, so I'd have to multiply the top and bottom by x minus 2. So that would look like this. X minus 2 times A over x minus 2 times x plus 5 plus the second term I have to times by x plus 5, so I get x plus 5 times b over x plus 5 times x minus 2, and that should be equivalent to what we started with. Okay, so far conceptually understand how we're setting this up. Now before we go any farther, I just want to point out this, when can you use this? Obviously you have to have rational expression. You got to be able to factor the denominator. You in AP Calculus, you will only get factors that are linear. In other words, like x plus 5, x minus 2, there's no exponent on here. They're linear. You could have a regular x out here, but you won't get like an x squared plus 5 inside here. One of the terms might be squared, like you could have an x plus 5 and then another x plus 5, but you're not going to get any quadratics or anything like that for factors. You would, and you could possibly do that, but we just, in AP, we don't do that. Okay? The other thing to write down and remember is, this only works if the degree of the denominator is greater than the degree of the numerator. Otherwise, we consider that we call it an improper fraction or improper rational expression. Okay, so the degree of the denominator must be larger than the numerator. So if it's the same or the numerator is even more, then you can't do this. Guess what we do first? What did we just get done doing? If the long division. So if not, use long division first. Then you do long division, and then you just do whatever you need. And one of the techniques you might need would be partial fractions, depending on what you get for your expression or equation once you're done. Okay, so here we are. All we got to do is really now figure out what a and b are, and then we'll have a new integral that we hopefully we can figure out. So we're going to solve this algebraically down here. The first thing you should notice is you don't really need to worry about the denominators. The only thing that needs to work out would be the numerators, right? That's all the only part you have to worry about. So we're trying to solve x minus 2 times a plus x plus 5 times b equals 4x plus 41. The other thing you may understand is this needs to be true for all values of x. Anything I put in for x at all, this needs to work, which is really great because that means I can put anything in for x and solve it. So the technique here is to let x equal a value, plug it in, and see what we get. Now, you want to pick values that would make your life much easier. What do you think would make your life easier? 0 seems easy. 1. 1 seems easy. There's two numbers that are even easier than that. If you think about plugging the value in and what would happen. Yes, if you put 2 in, if you let x equals 2, that's just awesome because this is now 0, and 0 times a is 0, so all of that part is gone. And now all you have here is 7 times b equals 2 times 8, or 2 times 4 is 8, 49. You get b equals 7. And the other number would make your life easier would be let x equal negative 5. So that's gone. I get negative 7a equals negative 21. A equals negative 3. It's really important that you establish a and b and write them down up here so you remember which one was which. Because it does make a difference. You have to get it above the right denominator. So a was negative 3, that's above my x plus 5. Plus b is 7, and that was above my x minus 2. And now we have that integral to solve, which is actually much easier. So, going right down the line here, each of these parts, these are partial fractions. Some problems in the AP test, like multiple choice questions, will just say, hey, find that, and on the homework, just find the partial fractions. Find the two fractions that would be equivalent to the one you had. That's all you had to do. It's like stop here. It's kind of nice. We're going to keep on going. We're going to find the integral. What are we going to do for this first one right here? Yes, use substitution. That's it. You have to. What are we going to let u equal? X plus 5. We're going to do this in our head because if we let u equal x plus 5, the derivative of that will be 1. Always check for that when you start doing these in your head. If there's a number in front of the x, then of course, if this was like 4x, the derivative would be 4, and you'd have a 1/4 out front. But this is just a 1. And so we know the derivative of that is 1, so we're going to end up dividing by 1, so that's beautiful. It doesn't do much. Negative 3 is just a little brother. So in our head, we can recognize this would be negative 3 times, in the 1 over u, that's going to be the ln of u, that integral of that. So it would be the ln of the absolute value of x plus 5. And again, if there was a number here, you'd have to divide by that. You get natural log for a lot of these problems. A lot of them. Plus, same story here. Let u equal to x minus 2. So we get 7 ln of u, absolute value u, which is x minus 2. Nothing in here to divide by, plus c. Okay, that is integration by partial fractions. And there's a beautiful shortcut to that too. That works sometimes. I wish I could take credit for it. It works a lot of the times, I should say. So let me show you that shortcut here. Alright, so we're going to go back to this exact same problem. We already have it factored. It looks like that. Sometimes you get problems on the test that are factored, sometimes not. If it's factored, immediately usually think of partial fractions. If it's not, just think about whether or not you can factor it. Okay, this is a trick that I've only seen one time in one book. And the book calls it the Heaviside method. And I don't know, maybe it's named after Mr. or Mrs. Heaviside. I'm not too sure. Not the most flattering of last names, but that's what they call it. Okay, so I can't take credit for it. Unless Heaviside was my nickname or something. Alright, so here we go. This is perhaps the most beautiful trick I've ever seen. Start with these two factors down here. The x plus 5, cover it over with your finger. Well, before you do that, look at it. What value would I plug in here to make this 0? Let's start with that. You bet, negative 5. That's obvious. So I cover it up. I take the negative 5 and I plug it into what's left. 4 times negative 5 is negative 20 plus 41, that's 21. 21 divided by negative 7 is negative 3. That's what goes above the x plus 5, the one you covered up.
Wow. You should just rebrand it as your own.
I know I should, but I think somebody might notice. Guess I could have lied to you and said I made it up. That's cool, isn't it?
Can you figure out a reason why that works?
Yeah, well, if you think about it, because what you're doing is you are, if you look it up here in terms of the math and the common denominator, it doesn't take too long to see how that we're always going to take this value that was the opposite and plug it in. The other one will be 0, so you'll be left with that other term times that a value, and you end up just dividing by that. So you can see kind of how that divided by the other one will work out. Same story here. 2 is what makes that to be 0. Cover up the x minus 2. The book actually had like a finger over, they drew a finger covering it up. I thought that was so cool. But anyway, so 2, put 2 in there, 8 plus, so 49 divided by 7, you get 7. So 7 goes here. Good question. When would it not work? It would not work if you have a problem that has a multiple root that has an exponent up here, or in this one, okay, on one of these terms. And I'll show you an example like that. Otherwise, it's going to work most of the time. And if it was an x out here, you know what I'm saying, then that would be a 0. You cover up, put a 0 on the other stuff, and whatever you get is that term. Okay? And that technique is perfectly legal on the AP test. Let's do another one to show you how much easier it is just doing that technique, or faster, I guess. Again, the hardest part is just recognizing what technique to use. You stare at that long enough and you realize there's not really anything that's going to help me out with U substitution or anything we've done. at all. Uncle Vester's not gonna, or Uncle Vernon, sorry, is not gonna help here. So we're gonna try to factor the bottom, and that works out. So I get x minus 2 and x minus 3. Now let's do the Heaviside method. So let's just write those denominators down first. Cover up the x minus 2, put 2 in, everything else. 1 over 2 minus 3 would be 1 over negative 1, so that would be negative 1. Put 3 in, cover this part up. 1 over 3 minus 2 is 1, so we get 1 here. So, use substitution. You're going to get negative 1 times the ln of the absolute value of x minus 2 plus the ln of the absolute value of x minus 2. Don't forget your log rules. You're kind of starting to remember that in the last assignment. Things looked a little different in the back of the book. You could very easily write this problem like this. And then when you subtract, how can you rewrite that with logs?
X minus 3 over x over 2.
You got it. So it looks like this. Okay. Let's do one that's, you can't use the Heaviside method. It's a little harder. This is about as hard as you'll see. So, we already have factored out. We could still look and think about use substitution. Don't forget about that. That's not going to really help us at all. So we're going to try partial fractions here. Now, here's the deal. When you have a multiple root like this, or multiple factor, I guess would be a better way of looking at it. It's a little unique on how you have to set this up. First, we have an x minus 1 here. We'll use a to go above that. And then for the other one, since it's squared, you need an x plus 2 term to be there. And then you need an x plus 2 squared term. So not another x plus 2 term, you need an x plus 2 squared term. And if it was cubed, you would need then another x plus 2 then cubed term. Okay? Again, you won't get any factors down here that have exponents on the x, but you could get a factor on that, and this is about as hard as you're going to get. And the Heaviside method doesn't work here. You might be able to play around and come up with your own shortcut. I haven't really thought about it too much. I just know that we've tried the Heaviside method, and unfortunately it doesn't work. All right, so that means we got to go the long way. We're going to get a common denominator. Think about our common denominator is this. So the a, that first term, we would actually have to multiply by the x plus 2 squared. The second one, you just have an x plus 2. So the b, you'd have to multiply by the x minus 1 and another x plus 2. And then the c, here you already have an x plus 2 squared, so you only need an x minus 1. And this needs to equal the numerator you started with. So now we have 3 values to find. So we take the values and make it easy. Let's just start out with x equals negative 2. Yeah.
Is it 3x minus 9?
Yeah.
Oh, it is. Sorry. Thank you. You caught that. That would have caused problems. Perfect. Okay. So negative 2, plug it in. That would be 0. This would be 0. You get just c here. So you get c. Negative 2 minus 1 is negative 3. Negative 3 times c equals And then this would be negative 6 minus 9 is a negative 15. C equals 5. Well, that worked out well. Then let's put in negative or positive 1. So that would be gone, that term would be gone. You'd have the a, put in this one, 1 plus 2 is 3, squared is 9. So 9a equals 3 minus 9 is negative 6. And you get a is equal to negative 2/3. And now we've run out of values that would, get rid of stuff or cancel stuff out. So now what do you want to do? Yes, we could put in a and c now, right? And we still have b, but then we have that x. So what do you want to use for x? Anybody got an opinion? Maybe 0 would be the easiest to use. You can put whatever you want in, really, but that's probably would be best. So, as Carmen said, we're going to put negative 2/3 in for the a. 0 plus 2 is 2. Squared would be, so this is times 4. Plus, and b we were trying to find. Put 0 in. So 0 minus 1 is negative 1. Times 2 is negative 2. So times negative 2. Plus, c is 5. 5 times negative 1 is negative 5. Equals negative 9. And you could add that in times, this is negative 8/3 plus negative 2b equals, and 5, we're going to get 4 there. Keep going, so you'd add 8/3 and divide, and you should end up with b is equal to 2/3. Okay? So, now we do the math. Plug it in, all those values in above. I'm going to just write it. I know this looks weird to write it like that, but just so you can see clearly where they're all coming from. A, B, and C. Go right down the line, use what you need. First one, use substitution. Negative 2/3 is the little brother. And you get the ln of the absolute value of x minus 1. Positive 2/3 out front. Ln of the absolute value of x plus 2. And that one. That is not the natural log. It is only natural log when you have just 1 over u or 1 over x. This is squared down here. So think of this as 5x plus 2 to the negative second. You will use u substitution and let u equal x plus 2. And the derivative will just be 1, so you're going to end up dividing by 1. So 5u to the negative second, we're going to add 1 to the exponent. Think of this just as u to the negative second. We're going to add 1 to the exponent and get negative 1, and we're going to divide by the new exponent. You can show all that work. Anyway, you would get negative 5x to the negative first plus c. So only use what you need. And don't overuse partial fractions. Any questions on this one? Yeah, Sigal.
Why do times b by both terms, but you only times a and c by one term? Or it's why does b have x minus 1 and x plus 1?
Can you say that again? I don't think I understand your question.
Right at the beginning when you set it up and you had a times x plus 1.
Oh, okay, way back up here.
Yeah.
Got it. Why did I only times which one by what?
Why does b get times by the other two terms, but a and c are only times by?
You have to do what?
It all comes down to what you have right now for your denominator. So here I have an x plus 2. This is my common denominator over here. So I still need to multiply by an x minus 1 and another x plus 2. Yeah. So always look at what you have and what your denominator should be. Do not overuse partial fractions. Only use it when you have to. I had a conversation with somebody this morning. They did a problem on the homework. I don't know, it looks something like this, I think. And they started factoring the bottom. X squared minus 1 times x squared plus or 1, right? And x squared minus 1 factors to x plus 1 times x minus 1. And they are stuck because they had an x squared plus 1. And Mr. Guy said you're not going to get one of those. So they factored that using imaginary numbers, which I said you'd never use this year. So that might have been a clue that something's going really strange. And did 4 pages of work and they got to an answer. What should you use here? Use substitution. Always try that first. Well, always try to do it in your head first and see if it's just one you know or memorize. Then use substitution. Then you reach into your bag of tricks and pull out another trick if none of that works, like partial fractions or integration by parts.
So when it says minus 5x to the negative first, it should be 5 times x plus 2 to the negative first.
Oh, thank you. Yeah. Glad you get that correct. Because that was you, right?
Yeah, I'm pretty sure.
Thank you. Yes, that's correct. Okay, so partial fractions, not too bad, especially with a heavy sign with it. Then we move on to the last section of this chapter, and that's 7.4, and it's entitled Improper Integrals. This is page 525. Kind of a strange name, improper integrals, like there's something, wrong with them, or they're not very nice or something. But really, it's just about integrals that involve infinity. This is going to start to blow your mind here. Some people are getting a little frustrated, but that's okay. I think it's just absolutely beautiful. Let's see what you think here.
I'm going to hate it.
So, you're going to do problems like this, where you're going to find the integral from 1 to infinity, let's say. One of your limits is going to be infinity. And let's do 1 over x squared dx. And we stop and really think about what the heck that means. If we graphed out 1 over x squared, it looks like this. If we go from 1 to infinity, well, this goes on forever and ever and ever. It's an asymptote. We're finding that area. Pardon me? You would think it might be. Not always. Sometimes it's like 2 or pi.
Oh my God.
Pretty cool, huh?
Okay.
Even though that limit goes on forever and ever and ever, we're going to take the integral and we're going to find the area there, and sometimes we're going to get a number, an exact value.
How can that even make it
What's the point of infinity if you don't get a value?
Isn't that crazy?
If it just keeps getting, if it never ends, how can there be
Yeah,
a
that's
number?
exactly-
Whatever, and x goes on forever, what's happening to y?
It approaches 0.
Yeah, it's approaching 0. It's getting really small. It's going to get to a point where it's probably unmeasurable. You know what I'm saying? You can kind of think of it that way in simple
It's
terms.
negligible on.
But the problem is, just because it approaches 0 doesn't mean you're always going to get a number. Sometimes you actually will get infinity.
Of course you will.
Sure.
I'll show you the difference in this. Told you, it's just going to blow your mind. All right, let's do the math. Now, this is infinity. Can you actually put infinity in? Is infinity a number? No, you can't actually put it in. So we're not talking about it equaling infinity. We're talking about it's approaching infinity. So we have to use limits here. Because it can't actually equal infinity, we want it to approach infinity. So we're going to take the limit, and let's use b for our upper limit there. So as b approaches infinity, and we're going to go from 1 to b, 1 over x squared dx. That's what you have to do. So you're talking free response problem, it's pain in the butt, write limit every time, but you've got to put limit in there and keep writing limit until we actually take the limit, which will be after we do the integral. If it's multiple choice, people like to just keep infinity up there, realize that they're not actually putting in, that's just they're taking the limit as it approaches it, which is okay. You can get away with that multiple choice, but not free response. So this is integral of x to the negative second, just to refresh your memory, not ln of x squared. So you're going to add 1, x to the negative first, divide by the new exponent, so you get negative x to the negative first. Or in other words, you get negative 1 over x. And we're plugging in b minus 1 as the limit of this as b approaches infinity.
Would you get the same thing if you like added 1 over 1/3 x cubed? Can you do it like that, or do you have to like switch it?
You got to switch it. Yeah, you can't just try a power rule on the denominator. That doesn't work. Okay, so we're gonna plug it in, and we're gonna get the limit as b approaches infinity. We're going to put b in first, so we get negative 1 over b minus, and then we put in 1, negative 1 over 1. And now we take the limit. We're going to put infinity in for b. What do you get? What is negative 1 over infinity? As this denominator gets bigger and bigger and bigger, what happens to the fraction? 0. So that's going to be 0. So this is going to equal 0 plus 1. Look at that. That's really cool. That area is 1. Huh?
That's cool.
And we can say, we can give this a value, we can say it converges. Okay?
What does that mean?
Well, what if it got infinity? What would you probably say? Diverges, yeah, right? So converges, diverges. We're just getting an idea of this integral is converging. It's going to be approaching an actual value. It's going to be equaling 1. Okay?
What does diverging mean? It's not approaching an actual value?
Now some of you are going to, diverging means it's not going to approach a value. So you're going to be just approaching infinity or negative infinity. It's cool. Come on, think about it. Then you really start thinking, well, how could you ever actually go to infinity? Would you never ever stop? So how do you know you're ever going to get something if you never ever stop? It's amazing, isn't it?
It's so amazing.
Let's do another example.
I like this. X squared.
Have you noticed that this like
Let's do 1 over x.
the kitchen table with like chairs?
Graph looks so similar over, at least in the first quadrant. Over here it's like that, but that doesn't really matter because we're just going from this case now 2 to infinity. So we're trying to figure out that. And you think, well, it should be the same idea as what we just did, right? Not necessarily. So we got to do the math. We're going to take the limit as b approaches infinity, 2 to b, 1 over x dx. You got to do it that way in free response. And integral 1 over x would be? So we get the limit as b approaches infinity, because I haven't taken the limit yet, of the ln of the absolute value of x. And we're going to plug in b, and we're going to plug in 2. So I get the limit as b approaches infinity of the ln of infinity minus the ln of 2. Oops, ln of b, sorry. I didn't plug that in yet. Okay. What is the ln of infinity? Well, let's look at the graph. As x approaches infinity, what is y approaching?
0.
Really? Is it going to come back down and go to 0?
2, 1, 1.
Stop guessing. Is there an asymptote here?
No.
No. This thing's going to keep going up. Even though it looks like it's leveling off, it just keeps going up and up and up. The ln of infinity would be infinity. So this is infinity minus the ln of 2. What is infinity minus a number? Infinity. Will this approach that area approach a a value?
Nope.
No. We say this diverges.
So what's the answer? Infinity or diverges?
Both. Diverges to infinity. You think about it that way. Okay? This is really cool. Later on, we're going to be doing problems, and I don't know if I'll save it for the last. I usually save it to the last unit we do. So save the best for last. We do the series, and we start adding up numbers. Remember series? You're going to find the sum of a series, and you start adding up an infinite number of values, and sometimes you get a number, like you get an answer. Like it's two.
That just makes absolutely no sense whatsoever.
No, it doesn't. Just do it right on the test. You're not gonna use it.
This
Did
doesn't
you?
make sense.
So, Carmen, did you say when are we going to use this? Is that what you just said?
No, so we're never gonna use this.
Yes, you are going to use this.
No, you're not. On the test, pretty much. Shut up.
Half of you used this every day last year.
What, in math class? It
Yes.
doesn't count when you're using it in
In
math class.
AP Stats.
I didn't use it.
All of statistics could not be accomplished without this concept. That's it. Let's take a look at this function right here.
This stuff or the series
And now we're going to do
could
this.
be accomplished without stats.
Now we're going to get crazy. We're going to take the limit from negative infinity to infinity.
Is that to the power?
E to the negative x squared over 2. That is all exponent. Yeah, just like that. Nice. At some point you got to start appreciating. This is pretty cool. I mean, think about this. If I graph this out, guess what it looks like?
Wow.
Beautiful.
Does that look familiar?
Yeah, it's a normal distribution.
Yes!
What is that?
It's the normal curve. Now, that's not the exact formula of the normal curve. I will show you the exact. This is the exact.
He's a shirt
No,
with
that's
it.
the,
Wait, what's the other shirt?
that's my jersey shirt. This is the exact formula right here of the normal curve.
I like that normal.
Normal, yeah. You like that? My
Wait,
sister
can we get
thinks she's professor at, teacher at, professor, associate, whatever, at UWGB. Teaches math. I don't know. You can't sell too many of these at the bookstore, I don't think, but that's where she got it. This is the real equation for the normal curve. Pretty close. This is a negative sign right here. It's kind of blended in with a fraction. Negative x squared over 2. So that part's the same. It just has this coefficient up front.
Huh.
What's the area under this curve from negative infinity to infinity? 1. It has to be 1. That's the whole concept of statistics, is that underneath that normal curve, the entire area is 1. Without that concept, you couldn't do any statistics that we have today at all. That is pretty cool. Now, if you were in AP Stats here, we get to let you know, you get to use your calculator and do normal CDF and find that area, right? Well, when I was in college as a math major, we had to take a statistics class that was calc-based. So if we wanted to find the probability or the area of the curve, we had to take the integral of the normal curve using, whatever limits that we had there. So go.
Wait, so with normal CDF, all we have to do, like, from one thing to another, is that just, like, the integral of it?
It would be the integral of this function right here. That's exactly what it is. That's what it's doing. Pretty cool, huh? So, there are a lot of applications of this, particularly statistics, and that's why it's important.
Like,
So it is
calculus book.
We are going to do this. We
Calculus
can do
is
this.
algebra that
We're going to
kills.
see what we get here. But here's the problem. We got one approaching negative infinity, another one approaching infinity. We can't take a limit as one approaches infinity and the other one approaches negative infinity. So what suggestions do you have about attacking this?
From 0?
Yes, break it into 2 pieces, probably right in the middle. Take one from negative infinity to 0 of this equation, and the other one from 0 to infinity. So you will have to be able to do this and recognize when you have both of them approaching infinity and negative infinity, you want to break it into 2 pieces. Okay, and each one of them you would take, in this case you would go the limit, let's say as a approaches negative infinity, from a to 0 of that equation, plus the limit as b approaches infinity, 0 to b of the equation. Okay, and you do each piece separately. Now this one actually, you haven't learned techniques to be able to, because if you think about this, you try u substitution and that derivative is not going to cancel and all that stuff. So that, at this point, you'd have to do on your calculator. But I wanted to show you, because I knew a lot of people were wondering when would we ever use this. I want to show you the actual equation that's, or pretty close to the actual equation that's used for the normal curve. Okay? Now, other improper integrals, other problems you run into. These actually end up causing the most problems because people stop and they forget about them. So this doesn't look too bad. Like if you were doing this in the AP test, you think, oh, this is easy. I'm going to just take an integral and throw in the numbers and it will be good. But then you got a problem. What's the problem here? Yes, 1 over 0 is a problem. If you looked at the graph, we're trying to go from 0 to 3. We're trying to find this, and that's going up to infinity that way. So that's a problem. You can't put 0 into this equation. So you would have to use a limit. The limit as a approaches 0, from a to 3 of 1 over x squared dx. Okay, and you go from there. Bless you.
Thank you.
Forever remembered. You look back when you're in college and watch the video and remember the day you sneezed in the video. You know what's weird? I can't tell you how many former students email me or call me or something and say, if it wasn't for your videos, I'd be failing in college. I can't believe people keep watching the videos, probably more after they graduate than when you're actually here.
If you post them on YouTube, you could become like a viral sensation.
You could be like Khan Academy.
Well, I only got like 7, maybe 27 views or something like that. Although I did get an email, I think it's a scam, that somebody said, hey, I've been looking at your videos, I really like them, you got a lot of whatever, and they want me to join their company to,
Teach math.
yeah, and how much you get paid for every 1,000 views, and I thought, yeah, I don't know, I get like 20 views. I don't think I'm going to make a lot of money on it. Anyway.
Like a penny.
I don't know, we like just like excited. We like
I don't even
smile.
If you put the log,
Yeah, if you start working.
Alright, once again with the same equation, 1 over x squared, we just keep using it because it's easy to graph quickly and see. We got a problem here. This is one that really throws people off in the AP test. Because you could easily do this, like the integral of 1 over x squared, well that's x to the negative second, so you know that's negative 1 over x, and you have no problem plugging 2 and negative 1 into those. So you would get negative 1, let's see, negative 1 over x, if you put in 2 first, it'd be negative 1/2, right? Minus a negative would be plus 1, so you get 1/2. I think I did that right. And you look and say, well, that's choice B, awesome, 1/2. Wrong. What's the problem here?
You can go from 0. Split up the integral.
Oh my gosh, they can really trick you with these. Look at this. Negative 1 to 2.
Wait, what? He said negative.
Like the AP test people.
I thought he said like, and then
What did you think I said?
It would go like that.
I hate children.
Oh, no, I love kids.
Kind of looks like a... You hate children? No. They don't hate children, they just want to make sure you're paying attention. So you have this point of discontinuity. This asymptote at 0. It kind of looks like it's going to go up like this. It kind of looks like a volcano here erupting. So that's a problem. You can't do it. You could plug it all in and get a number, but that's going to be wrong. What would you do instead?
-1 to 0.
You bet. And even if this was multiple choice, you wouldn't have to go through the trouble of doing the whole limit stuff, but you got to make sure that, because you can't plug 0 in here, so technically it would be the limit. So the limit is the integral from -1 to b, and this one would be like from a to 2, and you'd have to use the limit to figure that out. Okay? So don't forget those. Those will throw you off. I'll write all that in here. Approaches 0, -1 to b, 1 over x squared dx. This would be the limit. As a approaches 0, a to 2, 1 over x squared dx. Okay? Now, this book, I didn't see it mentioned in here, but some books mention, and I think it's helpful, they call a special improper integral. Because I know on the AP test this could certainly save you some time, consider it kind of a shortcut. And it would be, and I've used this one a lot here already, this idea. So it would be from 1 to infinity of 1 over x to some power. So p is just the exponent on x. So like 1 over x, 1 over x squared, 1 over x cubed, and so on. dx. You will know just by looking at that exponent if it's going to converge or diverge. And you can probably start guessing by the examples I gave you already. It's going to converge if p is greater than 1. So like we did x squared and it converged. And it's going to diverge if p is less than or equal to 1. And now you're going to see problems that have the integral 1 over x to the 1.5. Or 1 over x to the 5/3 or something like that. So that value will determine. Now here's the cool thing. If it converges, you can actually say what the answer is just by looking at it. The answer is going to converge to 1 over p minus 1. So the example I gave you was 1 over x squared, and remember that was 1, because 2 minus 1 would be 1 over 2 minus 1, or 1. If it was, in other words, this, 1 to infinity, notice this has to be 1, this has to be infinity, 1 over x to the 5th, dx, that's just going to converge to 1/4, because it's 1 over 5 minus 1. Okay? So that's kind of a nice little quick shortcut if you happen to get some, and they're more common than you think. And this actually, when we get to series, we're going to see a lot of them, to tell you the truth. So this is your assignment. Is there any questions at all? Problems. 20 math problems. I'm pretty sure I counted. 20. I'm pretty sure it's 20. So the first section, is all partial fractions, and the other one is all the improper integrals. And you have a ton of time. You do. 27, 28 minutes. You should be able to get a lot of this done. Alright, now you're going to get all freaked out. I'm just going to stop the video and